Alright guys, now we're gonna solve assignment 1 which is on your blackboard. We have a bent beam basically that has a diameter of 2.5 inches. We have a load that is applied on this cross section, and basically the load is 2.6 kilopounds, and we know the distance from the center of the shaft to the bottom is 12 inches on this side, and that distance is actually equal to 5 inches. So this is from the, so that distance is 5 inches. So we would like to find the stresses at element K and then H. So I'm gonna start by analyzing the cross section and basically mapping the forces and the moments into the cross sections. So what you have to do is basically you have to draw this cross section, sort of like, you know, amplify this cross section, and basically this is we have this is your cross section, this is our Z, and then this is our X. Alright, so we would like to basically map the forces into the cross sections into this, and basically we need to get the component of that force into here. So first we can start by looking at the vertical or the normal forces. So we're gonna have this guy, and I'm gonna call this F. What is F equal to? So if this angle is alpha, how do you know alpha? So we know tangent alpha is going to be equal to the opposite divided by the adjacent, so 5 over 12. Therefore alpha is going to be equal to the inverse tangent of 5 over 12. Then F is going to be equal to 2.6 times cosine alpha, right? So this is your force in kips. How about so we would actually have this shear force as well, which is basically that force mapped again on the cross section, and that will be 12 or 2.6 sine alpha. So V is going to be equal to 2.6 times sine alpha kips. Alright, so now we have F and V. What remains is we should look if that force is basically creating any torque on this cross section, and indeed it does. So the torque is going to be equal to what? To this component of the force, this component, which is equal to how much? 2.6 times sine alpha 2.6 times sine alpha multiplied by how much? Multiplied by this distance from here to here, right? So what is that distance? So that distance is given to us from the problem, which is going to be equal to 6 inches. So that distance right there is 6 inches. So 2.6 times sine alpha times 6 inches, and this is gonna be times kilopounds. So that number is gonna be in kips per inches, right? So now we have the torque. So the torque applied on the cross section is going to be equal to 2.6 sine alpha multiplied by 6 kips times inches. How about what else? So we've calculated the component of that force along this direction and then along the shear again. So this guy would have this component and then that component, and we calculated the torque and then the normal force, and then we still have the bending moment, right? So we do actually have a bending moment caused by that force over this cross section. So we have a bending moment that actually looks like that, right? So it looks like this, right? So that is your V, and that is our moment, and the moment is going to be equal to how much? The moment is going to be equal to this component of the force, which is equal to 2.6 cosine alpha, right? 2.6 multiplied by cosine alpha, right? So we got this component, and then this guy is multiplied by 6 inches, right? And this is again also in kips times inches. Right, so we have, this is your moment, this is your torque, that is your shear, and then that is the force. So usually when we have moments, we could have two moments. We have a moment in this direction caused by that, and then how about this guy? Is that guy creating any moment? So this guy is creating a shear, it's creating a torsion, but it is actually also creating a moment, right? If you think through it, that force is actually creating a moment like that. So we actually have another moment, and that moment is going to be like this. So what I'll do is I'm going to usually I like to refer to moments like that. So just put two arrows, and this will basically indicate the direction of the moment. So I'm going to actually bring this over to here and just disregard this sign. Okay, so that way we can keep all of them shown as vectors except for the torque. So again, this force, right, is trying to bend this guy like that, right? So like that. That force, right, with respect to this. Then what would be the moment? And how about the direction? So the direction of this moment is going to be like that. Do you guys agree? Right. So this is your moment, right? And then you can put the rotation next to it. You know, obviously it makes sense here, but this is what you have. So what is that moment, by the way? So that moment is going to be equal to this component, which is equal to how much? 2.6 kips multiplied by how much? By the sine of alpha, multiplied by what? Multiplied by that distance, right? You guys agree? So that distance from here, from this line to the cross section, and that is actually equal to how much? So we have total is 12, and then from here to here is 3.5. So 12 minus 3 is 9, minus 0.5 is 8.5. So that distance right there is 8.5 inches, right? Times 8.5 inches. Okay, so so it's pretty straightforward, right? So we have this is a moment. So that moment creates compression on this side, tension on this side. This moment create what? Compression on this side, tension on this side, and a net force creates compression. That force creates shear. And what we are interested in looking at, we're looking to look at the stresses at this element. One element is here, and then another element is there, right? That element is H, and that element is K. Okay, again, pretty basic. So when you have forces applied on a cross section, you have to map these forces back onto the cross section. So first of all, you're gonna decompose the force into Cartesian directions. So force along, for example, Z in this case, and then a force along Y, and that force basically you're gonna put it as it is, and then the second step. So we said that force gives me shear, and then that force is gonna give me a normal force. And because these two forces are not located exactly at the cross section, therefore they are going to be creating torques and moments. So this force will create torsional or torque, basically, that is trying to twist that cross section, and then that torque is going to be equal to how much? 2.6 times sine alpha, right, multiplied by 6, right, which is the arm of the torque. And that force is also creating a bending moment, which is like that, as I mentioned, and then there is this bending moment right here, which is equal to 2.6, right, 2.6 sine alpha, right, multiplied by that distance from the perpendicular distance between the force and the cross section, which is 8.5 in that case. And that is that. And for this force, it is creating a bending moment like that, which is equal to 2.6 cosine alpha multiplied by the perpendicular distance between the force and the cross section, or the axis of that cross section, which is going to be equal to basically this distance from here to here, which is given to us as 6 inches. Now that we have put the forces, moments, and then the torques, we can calculate the stresses that are involved on each element. I'm going to start by analyzing the stress on H. So again, that is a cross section. Let's do it a little bit in a clearer way. So this is your cross section, and this is one of the elements, and this is the other element. If you look at this element, let us look at what are the stresses that we are going to be observing on this element. So that is my element right there. What are the compressive forces? So here basically you can, for example, show the direction about or the orientation of this element, and here what we had is we had x, and then we had z, and then we had y. So if I'm looking at the xy plane basically, right, so I'm looking at this element from this side, so here I'm gonna have x and then y, which is, this is my x and this is my y and that is my z. So again, this is my camera view and I'm looking at this element like that. So basically what I'm going to see is I'm going to see compression from the top, right? Compression and tension, etc. So I'm going to, so then you're going to start with whatever that you have. So we have the stress caused by the force, which is compression, right? So F over the area, right? So we said we have the force F, and then we had the shear like that. This is your F, this is your shear, and then we have that bending moment. I'm gonna call this guy M, let's call it M1, and we have this bending moment right there, and then let's call this guy M2, and I'll let you guys replace the actual values that you have here. And we know this guy has a cross section area A, which is equal to how much? Pi over 4 d square, right? Okay, so looking at the force, so the force is going to create compressive stresses. Again, I'm looking at this element from this side, so I'm going to have F over A and then F over A. How about the bending moment? How about the shear force? Does the shear force create any stresses from the top direction? It does not. How about M2? So M2 is going to create compression or tension. So this is your moment, right? So if that is my moment, then this portion of the moment is going to be in tension. This guy is going to be under compression, right? So it's like I'm trying to apply that over here, right? I'm trying to twist that like that. So this would be in tension, and then this would be compression, right? Compression is going to be in a direction of rotation of this guy, right? So it would be plus M2, right? We know that the stress is equal to MC over I, right? So MC over I. What C is in this case? C is going to be equal to D over 2 in this case. C is going to be equal to D over 2, and I is going to be equal to how much? Pi over 4, right? Diameter C to the power 4, right? Okay, I is equal to pi over 4 C to the power 4. Okay, so we know C is half the diameter, and that is your I. How about the stress caused by that moment? Does it create any moments? It does not create any stresses. So that moment creates no stresses relative to this element. This guy will only create tension, and then the force is going to be, so the force is basically compression, guys. So this has to be minus, right? So minus. So minus F over A plus M2 C over I. How about here? Same thing, right? So this is minus F over A plus M2 C over I. Alright, how about stresses in that direction? Do we have any stresses in that direction? We do not have any stresses in that direction, so these are 0. So if anything, we may have shear. So we forgot to include the torque, right? Right, the torque, which was equal to 2.6 sine alpha times 6 from the previous slide. by looking at the torque right now, we can get the shear. What is the shear stress applied on here? So the shear stress will always be in the same direction as the torque. So the shear is going to be like that, right? So all the shear here is going to be like that, right? So that is your shear. All right. So the shear is going to look like that. What is the value for the shear? Is going to be equal to what? TC over J, right? We know the value of the torque, we know the value of C. How about J? J is going to be equal to how much? Pi over 2 C to the power 4. And that is it for the first element. So this is element H. Okay guys, any questions on that? Please let me know, and I'll be happy to go over this again with you. Again, so the force is creating a negative stress because it is compression. How about V? Does V create any shear stress in addition to the torque? It does not, right? We said the maximum, or the shear caused by shear force, is going to be maximum at the neutral axis, like here, right? And it will be 0 at the top, right? So we've already discussed that. Okay, so now let us look at the other element, and I want to actually try to put the other element over here. And now let us look at element K. And how about this? So how am I looking at that? So I'm gonna look at this in a Y and then Z plane, right? So we're gonna look into this from this direction. So Y and then a Z plane. So the top is Y, and then that guy is a Z. And here it doesn't matter much the direction of the Z, because you're gonna get basically the same shear. All right, what are we going to see if you look at that? How about the compression due to the force F? It will be always, again, minus F over A, so that won't change. Alright, so we started with the force F. How about the bending moments? Does M2 create any moments? Sorry about that, so sometimes here my view is a little bit small. So the stress caused by the force on this guy is negative, right? So I already put that, so we're done with the force. Now let's go to the moment M2. Does M2 create any moment or any stresses on that? Any axial stresses? It does not. Why? Because it is located along the neutral axis. How about M1? So M1, it does create compressive stresses. Why? Because that M1 basically will put this region in tension and then that region here in compression, right? So here it's going to be minus, right? Minus M1 C over I, where you have the same values of I. How about any other compressive forces? So only we are going to have M1 creating compressive, F is creating compressive, and that is really it, right? How about the shear forces that are applied on here? So the shear forces, we are going to get shear forces. So one of the value of the shear is going to be equal to TC over J, right? We know the torque, we just calculated torque earlier. C is equal again D over 2, J power over 2, C to the power 4, as it is a circular cross section. And what else do we have going on here in terms of shear? We actually have a shear caused by that shear force, right? We have a shear caused by that shear force because this is located at the neutral axis. So here you have to add plus what? VQ over IT, right? And what is the T in this case? The T is going to be equal to the diameter, right? I is going to be equal to, we just calculated I already. How about the Q? So Q is going to be equal to Y bar times A, right? Where Y bar is what? Y bar is going to be equal to the centroid, the distance between the centroid of that cross section. So this is your V, right? This is our V. So we're gonna get Y bar, right? So Y bar is gonna be the distance between the neutral axis and the centroid of this cross section, right? So that is going to be y bar, and I actually provide an equation for this guy for you guys earlier, and the area is going to be the area of this guy, right? So it is half the circle in that case. So the area of half the circle is going to be equal to how much? Pi over 8d squared, right? Or pi d squared over 4 divided by 2. Okay, how about y bar? So we are looking at the centroid of a centroid of a mini circle, of a half a circle, right? And we actually have that from our notes. Y bar is actually equal to 4c over 3 pi, right? Okay guys, so that is really it for this element. So we have a shear basically, which is caused by the superposition of the torque and the shear stress, right? So here the shear stress caused by that guy is going to be like this, right? So that is the direction of your shear. That guy is Tc over J, right? And then the shear force itself, V, will basically create equal shear forces here, right? And the value of this guy is going to be equal to VQ over IT, where I is equal to pi over 4 C to the power 4, where C is equal to D over 2. And we have these values that we calculated based on the equations of the shear, transverse shear, and then the shear based on the torque. Alright guys, so I would let you guys crunch the numbers on this one, and that is what you have to be doing on this types of problems. Alright.